Hi, this is day 49, and today's episode is brought to you by the letter B, which of course stands for magnetic field. And today we want to talk about something called magnetic flux. We want to talk about induced currents, and we want to talk about generators. Before we do any of that though, let's take a look at something we touched on last year, and that is how an electric motor works. What I have here is an electric motor, and of course it's hooked up to a power source, and you can see that if we give the electric motor a little bit of juice and we give it just a bit of a nudge, because it's not the most cooperative electric motor in the world, it starts spinning around like crazy. And it looks like it's trying to make an escape, so we'll back off on the juice, we'll shut it down. And yeah, how exactly does an electric motor work? Here's a good close-up of the electric motor. It'll let us explain exactly how it works. Now, the current gets fed into the electric motor, and some of the current feeds this electromagnet, and you can see there is one pole of the electromagnet, and on the other side there is the other pole of the electromagnet, and that electromagnet is of course stationary. It's what we call the field magnet, and inside the field magnet you can see we have this piece of apparatus which spins around, and that piece of apparatus that spins around, if you take a close look, you can see that it is basically one solenoid or coil, and perpendicular to that another solenoid or coil, and the current gets fed into those two coils. And you know, of course, when a coil like that is fed a current, it becomes an electromagnet. So there's essentially two electromagnets here. There's a field magnet on the outside, and there's the spinning electromagnet, which is called the armature, on the inside. And of course, the attraction and repulsion between the field magnet and the armature, well, that's what causes the armature to spin around. Okay? So there you have it. Now you know how an electric motor works. An electric generator is basically the same as an electric motor, except with an electric motor you feed current in and you get motion out, but with a generator you put motion in and you get current out. Well, before you're looking at an electric motor, now you're looking at a generator. Okay? And yeah, essentially they are the same thing. You'll notice we have in any generator a field magnet. Okay? Now this field magnet is actually an electromagnet. It really needs a current put through it to work at peak efficiency, but to be perfectly honest, it just had a current through it a little while ago, so there's still some residual magnetism in there. So this field magnet, it still has enough of a magnetic field to make things go. And yeah, any generator, it's going to have a field magnet, and it's going to have a armature inside it. And an armature is basically just a solenoid or two that are free to spin. Okay? And this generator, it is hooked up to a galvanometer. I'll try that one more time. It is hooked up to a galvanometer, which is a device that detects very small electrical currents. And you can see when the armature spins around, when those coils spin around inside the field magnet, you get a fairly significant current. Okay. And of course, if you spin in the opposite direction, you get a current going in the opposite direction. Okay, so this is a generator. It induces a current. And of course, that's how hydro supplies our houses and our buildings with electric current, with a generator. Batteries are great if you just got a small little electric circuit, like maybe a car or whatever. But if you want to supply large amounts of electric current to a lot of different loads, then you probably want to use a generator. And the generator that Manitoba Hydro uses, or the generators that Manitoba Hydro uses, are not a lot different than this thing right here. And we're going to see how exactly these work. What we have here is a really crude generator. As you can see, it consists of a coil and a bar magnet, and it's hooked up to a galvanometer. And you can see that when the magnet goes into the coil, you get a current. When the magnet comes out of the coil, you get a current the opposite way, and so on and so forth. But you'll notice that if the magnet just hangs around motionless inside the coil, you don't get any current at all. Now, of course, this is a really crude generator. It's not nearly as efficient as the spinning generators that we were just looking at, the spinning generators that Manitoba Hydro uses. But if you can understand how one of these things works, you can understand also how one of those spinning generators works. So we'll go to the board and we'll explain how one of these things works. To know how a generator works, first you have to know a little bit about something called magnetic flux. Magnetic flux is abbreviated with the Greek letter phi, and you calculate magnetic flux by taking magnetic field and multiplying by area. Of course, not just any old magnetic field, not just any old area. You'll notice there's a perpendicular sign beside the magnetic field symbol. That's because you need the component of the magnetic field that is perpendicular to the area. And of course, the area is the one that the magnetic field is projecting through. So there you have it. Magnetic flux is equal to magnetic field times area. And if you're going to induce a current, magnetic flux has to change. Now, let's see how that works when we're talking about this situation right here, where I induce a current by going like this, okay? So, first of all, you have to remember that the magnetic field that is projecting through the area, well, that's constant, right? That's the area of that circle, and that's not changing. And you also have to realize that the magnetic field, well, it's directed straight up and down, so it's perpendicular to the area, so we don't have to worry about components. But you also have to remember that as the magnet gets closer to the coil, the magnetic field inside the coil is increasing. As the magnet gets further away from the coil, the magnetic field inside the coil is decreasing. So as I do this, the magnitude of the magnetic field is changing. It's getting stronger, it's getting weaker. Okay. So look at flux. Flux is equal to magnetic field times area. Now remember, if you're talking about one of these things, the area is staying constant, but as that magnet goes in and out of the coil, the magnetic field is changing. Because the magnetic field is changing, flux is changing, and yeah, you get a current induced. Next thing we'll take a look at is how exactly a spinning generator operates. Okay, so magnetic flux is equal to the magnetic field times the area, and to induce a current, flux must change. So how on earth is it that flux is changing when you're talking about one of Manitoba Hydro's generators, where the water comes through the dam and it spins the armature around like so? How does flux change in that situation? Well, let's take a close look at it. So essentially what's happening when this is going on is the magnetic field is going from the North Pole to the South Pole of the field magnet. The magnetic field is making a straight line like this, and the loop is rotating, or the loops, because there's a coil there, so there's a bunch of loops, right? the loops are rotating like this. So let's take a close look at that. So the magnetic field is like this, and the loop is rotating like this. Okay? What's going on there is depicted in these three diagrams right here. Here we have a side view of the area, and there's the magnetic field headed straight across. And when the area is aligned like this, well, the entire magnetic field is perpendicular to the area. Remember, when you calculate flux, you need the component of the magnetic field multiplied by the area. So here, the entire magnetic field, well, it is the perpendicular component. Okay? If the area gets tilted a bit, and that's what happens when it rotates, it tilts a little bit. Well, now take a look. If you split the magnetic field up into components that are parallel and perpendicular with the area, okay, well, you can see the component that is perpendicular to the area, well, it's a little bit smaller than it was over here. Okay? And if the area continues to rotate, and again, you split the magnetic field up into perpendicular and parallel components, well, the perpendicular component, it gets even smaller. So as that area is rotating, well, the component of the magnetic field the component of the magnetic field perpendicular to the area, it changes. Therefore, the flux changes, and yeah, you get an induced current. So there's no assignment to go with this, just make sure you understand it, and tomorrow you're going to see your last test. There will be a question or two regarding magnetic flux and induced currents and generators, and of course everything else that we've done in this unit on electric circuits. It'll be shorter than most of your other tests. It's basically just going to be the exams questions that pertain to this unit, and it should be posted by noon, and it will have to be handed in Monday morning, I believe. Check the instructions on the test tomorrow for details. Good luck. We will see you later.